9.6 surface integrals. Let's assume that you have a parameterized surface already, right? And you're getting area. Before we move on to surface integral, we start from basic concept, okay, of the integral. So we're getting area of parameterized surface. Then you have to recall the area of parallelogram, which is this, right? If you have a two vector, right? And the area of the parallelogram is this, right? That's this. The length, the absolute, or determinant, the absolute value of the cross product of two vectors. Okay? That gives you exactly the area here. Okay? All right. Having said that, let's look at this, picture. We have a surface S, right? An arbitrary surface in X, Y, Z, and we're going to differentiate a very, small portion of S, which is ds, right? And then we assume that this is our u direction. This is a tangential to the, tangential plane to the surface, okay? This is tangential. Tangential. Okay? And that's the direction of r sub u. Okay? It's r is here. This one is r of, uv. Okay? This is a position factor. And this is the direction of the u direction. Okay? U axis direction. And let's say this one is v axis direction. Then if you multiply the scalar value delta u or delta v, that's the amount of the vector. Okay? That's what delta s is. ds or delta s, yet, right? And you make delta to be 0, right? You make delta s to go to 0. I mean, before you do that. And delta s is this one, right? That's the parallelogram, the area of the parallelogram. This is the area, right? This is small area. And so this is a parallelogram of the area, right? And you can take the scalars out, right, from the cross product, right? And then that's what it is. So it's ts is r u cross rv du dv. Okay? All right. So area is you integrate every ds. You add all the ds, right, over the region, right, and that's this. Okay, dA is du dv in this case. All right. Okay. I'm going to give you an example first. This is that. Okay. This is 2, 3, and that's 4. So when you have a surface, you have to, find choose the appropriate coordinates, right? So let's take the cylinders. This is a cylinder, so let's take cylindrical coordinates. 3 sine u, comma, v, and from 2 pi to v to be 4, right? So the area is, we just, learned, this is double integral, and RU, RV, and du dv, right? Okay. And that's actually the Jacobian. You remember? This is actually, from dxy to xyz to uv coordinates. Okay? So actually that's the Jacobian. All right? But anyway. So you have to get RU and RV, which is, in partially differentiate this one with respect to u. minus 3 sine u, 3 cosine u, and 0, right? And RV is partially differentiate this with respect to, V, that's 1. Okay? And RU cross RV is I, J, K, and minus 3 sine u, 3 cosine u, and 0, 0, 0, 1, right? And if you calculate that, that is 3 cosine u, comma, 3 sine u, comma, 0. Okay? And the length of this factor is RU cross RV is, this one square, and add them up. So cosine square, sine square is 1, so this is 3, right? So A is from 0 to 4, 0 to 2 pi, 3 times, okay, that's the Jacobian, and du dv, right? So from 0 to 4, that's 3u, 0 to 2 pi, dv, and from 0 to 4, 6 pi dv, that's 6 pi v from 0 to 4, 24 pi. We have another, application here, right? The surface area of when z is function of f of xy, where z is given of, function of xy, like that, right? Then, in this case, dx dy is okay, right, to calculate the area. Then in that case, that's what it is, right? And r is this, right? And r sub x is this. R sub y is this. And the area is the Jacobian times dx dy. And that's the, So I'm going to move on to surface integral now. All right? And if you remember from line integral, you had scalar field case, right? And vector field case. Okay? And we have same stuff for surface integral for scalar field. Okay? If a scalar function is given like that, f of x, y, z, and ds is, this is function of f of uv simply. Okay? And Jacobian. Alright? And du dv. Okay? So you can understand it from, extension of the area. You have function is multiplied here as an integrand, right? Before, area is, there's 1, right? Here, the integrand function was 1. And now we are generalizing this area calculation to surface integral, okay? By having scalar function there, right? Okay. Okay, let's take an example. All right. So, let's take the integration of x, y, z, 3D, and ds for f of x, comma, y, comma, z is x, y, and the surface is x squared plus y squared is 4, and 0, z, 8 in the first octant. X cylinder, x is 2 cosine u, y is 2 sine u, z is v, So u is from pi over 2, v is 8. Okay? And r of uv is 2 cosine u, so 2 sine u, comma v. And let me just, r u is minus 2 sine u, 2 cosine u, 0. rv is 0, 0, 1. And you calculate it. Let me just write the answer. You can try it on. Okay, it's 2. And so the integration will be from 0 to pi over 2, 0 to 8, 2 times cosine u times 2 times sine u times the Jacobian 2 dv du. The answer is 32. This is a simple double integral, so you can do that. Next one is vector field, okay? So when there's a vector field, when there's a surface here, right, we have vector field on the space, right? And we want to get, let's say, this is, the normal vector, right, of the surface, right? It changes, upon the position of the, surface, right? And let's say this one changes like that, this one changes like that, okay? And that the red, arrows are the vector field that's passing or existing on that spot, right? But what we want is not the vector, whole vector, but we want to have that projection onto the surface normal, okay? So that amount is that amount, and that's this amount, and that's projected here, so that amount, that amount, that amount. So we add those, projected amount all over the surface. That's what the surface integral of vector integrals. If you recall the line integral for vector field, you have the same thing, okay? Same stuff. All right. So the surface integral over the vector field, and we want to have the surface normal, okay? Normal vector, that's a direction vector n caret, okay? And then that's this. This is Jacobian. Okay? Because we are transferring from x to y to du dv. So we need Jacobian, okay? And that is, simply this one, right? You remember that? And from this relationship, we can have this one. Okay? So this one is the most, the formula that you use most often, okay?